name's Dan Gottlieb. I run a small consulting firm focused around building real-world projects using FHIR and also working on some standards to support those projects. And I'm really excited. It seems like we have a great turnout. I'm excited to be able to tell everyone or talk to everyone about a project that I've been working on for almost 2 years now called FlatQuack, which is a SQL-on-FHIR implementation targeting specifically SQL in DuckDB. And we'll talk a little bit about what DuckDB is. Arjun gave some great pointers, and we'll go into a little more detail for folks who aren't familiar with it. Let's see here. And then, so kind of structure-wise, we'll talk a little about a little about DuckDB, a little about FlatQuack, and then we're going to do, kind of following Steve's lead, a very high-risk live demo that hopefully will work. So it should be interesting regardless. So DuckDB, as Arjun mentioned, is a fully open source, fast in-process analytical data engine. So if you're familiar with SQLite, which is kind of an in-process transactional SQL engine, DuckDB follows the same philosophy, but is really focused on being able to do large-scale analytics very quickly. In the upper right of the slide there, you can see Hannes Moheisen, who is the university professor who created DuckDB. And you can see his pet duck on his shoulder, which is how the project got its name. DuckDB's been around for a couple of years. They recently released version 1.4, which has some really good performance improvements. And it has community support as an open source project, and also through DuckDB Labs, commercial support, as well as a number of commercial companies that have built different implementations that folks are adopting for when they want to use DuckDB. And one of the things that's really neat about DuckDB is it's what I would call a batteries included database engine. So it can read and write a lot of different data formats natively. So it has support for kind of common data formats like NDJSON, Parquet, CSV, and then kind of a native DuckDB database format. And all of those were written from scratch for DuckDB. So they didn't use existing libraries, but started designing these data readers to be super efficient on modern hardware. So being able to use multi-core chips and have an architecture that works really well with optimizations that the processor can apply. So the ability to read and write these files is really performant. Another neat thing that DuckDB does is that it supports reaching out into other databases and accessing data there without having to convert your data first. So you can connect a DuckDB instance directly into Postgres or into MySQL, or read SQLite files directly. And it does something called predicate pushdown, where in your query, if you only need a subset of the data in Postgres, it'll query Postgres for just the subset of data that's relevant to the query that you're doing within DuckDB, and just pull back that data and then analyze it within DuckDB. So it can be pretty efficient at doing that too. This is also a good time to talk about what an in-process analytical data engine means. So in contrast to, for example, Postgres, which is a server-based database, you would have your application reach out to Postgres through a protocol and connect that way. DuckDB actually runs embedded within your application as a data engine. And so you don't have that overhead of connecting to an external database. There are some trade-offs in terms of scalability, and we'll talk a little bit about that, but you also get that kind of really fast performance on local data sets. DuckDB also includes data lake support, so you can query directly against a set of Parquet files that are stored in Apache Iceberg format on S3 or on some other cloud data store. If your data format's in a Delta Lake format, which is kind of a parallel data lake format to Iceberg, you can query directly there. I think they were still working on writing to Delta Lake, but you can read easily. And then there's a new format that the DuckDB people put out called Duck Lake, which is if you're building a lake from scratch, you can use kind of a native DuckDB format. And all of these things can live in the cloud while the DuckDB piece lives locally on your system and queries out to it. So DuckDB can read and write a lot of different data formats. And then the other thing that turns out to be really, really interesting is that DuckDB works really well with FHIR data. So from the start, DuckDB has supported nested data. So Arjun in his opening talk this morning mentioned that one of the challenges with working with FHIR is that it's deeply nested data. And many databases kind of struggle with that or have some bolted on ability to work with those nested types. DuckDB from the start has a list type, which corresponds to like arrays in JSON, and has a struct type, which kind of corresponds to objects in JSON, and is able to kind of very efficiently work with those data structures. So it turns out to be a really good fit for working with deeply nested FHIR data. I mentioned they developed their own NDJSON parser, and As a couple folks have mentioned, when you do a FHIR bulk export today from a clinical system, the output tends to be in NDJSON. And so it's a really nice fit here where you can get your FHIR data out in bulk in NDJSON, and then you can process it using these really efficient NDJSON readers on top of DuckDB. DuckDB also has a couple of SQL features that are really good for working with clinical data. One of them is it does something called fuzzy temporal joins, where you can kind of look for an event that happened before another event and join two tables based on the event happening before a different event or after a different event. So if you want to look for something like a medication that was ordered prior to a procedure, and those are in two different tables, you can use these fuzzy temporal joins. And you can do this in a lot of databases using things like window functions, but in DuckDB, they've kind of optimized this specific use case. Another use case that they've optimized that's also really common in healthcare is looking for the top few values within a group, or the few most recent values within a group. So if you want to pull the patient's last 5 A1C lab results, there's a specific operator in DuckDB to be able to say, I want those lab results. And again, this is something you can do in almost any database, modern database engine, but in DuckDB, it's optimized with a kind of a high performance path. So these features make DuckDB really good for working with clinical data, particularly once you've flattened it. And DuckDB, if you have a lot of RAM to throw at a problem, DuckDB can be really performant. And in recent versions, they've really worked on optimizing larger than memory performance too. So I guess I've been able to process. So I would say DuckDB really is kind of ideally suited for kind of medium-sized data, small to medium-sized data. So if you have, a couple 100 million FHIR resources, you can process those in a minute or two in DuckDB. Once you get into billions in your data lake, as long as you're querying subsets of that using parameters that can be using a well-partitioned Parquet data store, that can be efficient. But if you really need to read over very large data sets, probably you want to move to a different type of database engine. So shifting gears to talk a little bit about FlatQuack. FlatQuack, like DuckDB, is fully open source. And there are kind of two ways you could think about building a view runner for SQL-on-FHIR. The first way, it would be an engine where you run it and it kind of loops through your data and processes it against that view definition, all inside the view runner. And that has some advantages because it makes it very easy to support new FHIR path features or complex processing. Another way you can do it is, and this is the way that FlatQuack works, is actually compile the SQL-on-FHIR view definition into just regular SQL. So I'm going to show you a command line tool for FlatQuack, but what it's doing is not actually processing your data. Instead, it's just taking that view definition and writing out SQL that works within DuckDB, kind of with any DuckDB runner. And this is really powerful because it means that you can take your SQL-on-FHIR flattening definitions and put them into kind of a standard data pipeline that you're already using or want to use as an orchestration tool. So something like DBT or Apache Airflow, kind of both can kind of directly integrate the SQL that comes out of FlatQuack. FlatQuack also has a feature called SQL pipeline templates, which lets you customize the SQL that comes out of it to kind of fit your data needs. So in our demo, we'll be looking at an example that reads NDJSON files and outputs CSV files, but you could tailor that, and you could actually not talk about inputs or outputs if you want in the SQL and use something like a DBT source in your template that then would just kind of slot into your data pipeline. So FlatQuack will do this compilation. You get out SQL. You can use any DuckDB engine to run that SQL. And many of the common database workflow engines support DuckDB natively now. And the data that comes in can be NDJSON, but it could also be FHIR data that you have stored in Postgres. It could be FHIR data in Parquet. Basically, anything that DuckDB can work with can be an input into your compiled view definitions. It outputs flat tables, and then as some of the other presenters have mentioned, that's really a great input into the rest of your SQL pipeline or directly into BI tool if you're kind of at an end state. So the goal of compiling to SQL here is really to fit well into existing workflows. There are a couple new features in FlatQuack that we added recently, and I want to highlight some of those, and then we'll do a demo that includes a few of these. The first is support for DuckDB 1.4, which required some tweaking in the SQL generated because of some changes there. But once we got that working, it really improved performance. So DuckDB team has been working really hard at improving performance for large data sets, and we're able to take advantage of that work with our compiled SQL. So FHIR paths, which are kind of inside your view definitions, are able to have variables in them. So for example, you wanted to pass in some terminology codes at runtime or at compile time in our case, you could have placeholders in your view definition in the FHIR path and then pass those in from the command line. So we now support that in FlatQuack. And then kind of a really cross-platform way to use SQL-on-FHIR is to have a couple view definitions, compile them into flattened tables, and then have some standard SQL that runs on the flattened tables. And Nikolai talked about the library query approach that we're going to be taking going forward, and that's a really good fit for that. But there are also cases where you might not want to materialize your FHIR into a table before applying some SQL to it. And so we added an experimental invoke function recently to FlatQuack. This is in response to a production use where folks really needed this, that lets you kind of mix some SQL into your FHIR path and execute any DuckDB function or macro as part of your SQL transformation. And so we'll look at that in the demo. So it kind of depends on your use case. If you are doing something where you're experimenting or something that's specific to your implementation, you could use this functionality. If you want something that's going to run cross-platform, probably the forthcoming query resource might be a different way to use the same SQL, but apply it in a more general purpose way. So I'm going to shift to a demo. This demo is based on a real world use case. So I had an organization that needed to report some flattened anonymized FHIR data to a third party. And so they ended up using FlatQuack to do that. I've simplified this. We're only going to look at demographics, and we're not going to look at the full set of transformations, but this is kind of a real world use that you could apply FlatQuack to this today. So when we talk about a flattened patient list of demographics, what we're going to try to pull out here is the patient ID, the birth sex of the patient, the birth date, and the postal code. And on the right here, hopefully this is large enough for folks to see, is a sample patient resource. And so we can find these elements in there. So we're going to pull the ID directly from the resource. We're going to dig in and find an extension for US core birth sex and pull out the birth sex. And I have to apologize a little bit for our global audience here. This is a little bit of a US-centric example because that was the project that I worked on. But the same patterns apply kind of with data for any locality. Birth date, we're going to pull out, that's the kind of the easiest element. It's right in the resource. And then lastly, we want to pull out the postal code for the patient to report as part of our anonymized data here. And this is interesting because a patient can have more than one addresses, and we want to pull out every postal code that's listed for every patient. So we're going to write kind of a view definition to do that. And that's going to look like this. So you can see we're pulling out the ID, we're pulling out the birth date, we're digging into the extensions to find the birth sex extension. And then for each or null, we're kind of looping through the addresses and pulling out the postal code. So let's shift here to an editor. This is Visual Studio Code. And you can see I've created a new project here with literally one file in it, which is just an ND-JSON file of patient resources. And I generated this using the Cynthia synthetic data generation tool, but this would be the same type of file you would get using a bulk export from a FHIR server, which is kind of how we did it in the real project that I'm demoing here. So the first thing we need to do is create a view definition. So I'm going to, just to save time, copy and paste that view definition from the slide. But all of this is being done live. There's no hand waving here. So we'll save this as patient flat anon. And I like to call my view definitions.vd.json just so that I know which JSON file they are. So we've saved that. We've got that here. And now we're going to run FlatQuack. And you can install FlatQuack locally, but to tempt the demo gods, we're going to try to pull it down live from a package manager. And we're using a tool called Bun, which has the ability to directly pull something down from the package manager and run it. Bun is a JavaScript runtime environment. And interestingly, as a side note, on Tuesday, it was bought by Anthropic to power their JavaScript, the JavaScript tools for their LLM. So things like Claude Code. And so it looks like it's going to have long-term support, which is nice. Although pretty much any FlatQuack could be run in any JavaScript engine, including some things like Node. So we're going to use Bun to do it. We're going to say we want to use the FlatQuack package, which is on NPM. Oops, FlatQuack. And then FlatQuack lets you do different modes. So you can actually, by default, it'll just show you the query that it's generating in the command line. We're going to actually tell it we want to use the build mode to output a file because I think it'll be a little easier for this demo for folks to see. So we're going to run that. It's actually pulling down the package here, and it compiled our view definition here to a view definition.sql, and it did that in the same directory. So we're taking advantage here of a lot of defaults. So by default, it searched for any JSON files in this directory, and by default, since our view definition mentioned that we were looking for patient resources, it looked for any ND-JSON files that had the word patient in them. Of course, all of this is customizable by the template you're using, and you can actually pull in different templates that do different variations of this as well. Everything's customizable through the command line, which view definitions it's running, which directories it's looking in, all that stuff. But we did the simplest possible version here and got the SQL file. I won't go through the SQL in the interest of time, but I did want to highlight kind of one piece here, which is that FlatQuack is extracting a schema from your view definition. And that'll include both the elements that are going to be output and elements that are used in filtering for that output. So things like where clauses. And so what it's doing here is, if you look at address, right, address in FHIR has a pretty extensive schema with a lot of elements, but we've created a sub-schema here where we're only pulling out postal code because that's the only value we need to read into DuckDB in order to be able to kind of run this view definition. So it's kind of another performance tweak where it's actually just filtering, it's just querying the values that are relevant for your view definition. Another thing that's interesting here is it has full knowledge of the FHIR schema. So even though we didn't tell it in the view definition that address is an array, it read through the FHIR schema, realized that that was an array, and created an array of structs with just the postal code value in them to extract just the relevant pieces. So there's a lot of optimizations that kind of happen behind the scenes when you compile to SQL here. So now I could run the SQL in, kind of any SQL pipeline tool that I'm already using and have those files then flow into other steps in the pipeline. For our demo here, I'm just going to change the build to run, and we're going to use kind of a built-in runner within FlatQuack to generate a CSV of the flattened data from this patient.ndjson file that we were looking at. So again, pulling down the thing, 25 milliseconds. We only have about 120 patients in that file, so it's pretty quick. And we can see we got this flat_anon.csv, and it's pulled out the ID, the birth date, the birth sex, and the postal code for each of the patients in our source data. I don't think any of those patients had more than one address in the generated data, but if they did, you would get 2 rows that repeat all the data except for the zip code and provide the second postal code as well. So now I'm going to shift back to the slides because we forgot one other piece of our demo, which is that we also want to de-identify this patient list. So we don't want to send this exact list to our third party. We want to do some de-identification first. So we want to first obfuscate our FHIR identifiers. So patient ID is not a patient identifier per se. It's an identifier of a resource in our EHR. But at the same time, it's kind of good practice not to pass along any of those values to a third party. So we want to at least obfuscate that. For birth date, we want to drop the month and the day if it's present, and just keep the year to, again, make it harder to re-identify patients from our data set. And then for postal code in the United States, postal codes can get pretty granular. And so we only want to take the first 3 digits of the postal code to make them less identifiable. There's a trick. Of course, we only want to do that if it's a US postal code, not for other postal codes. In this particular use case, the third party only needed to see postal codes for patients who are based in the US. And then the last piece, which is even more tricky, is that we only want to take the 3-digit code if it covers more than 10,000 people. If it covers less than 10,000 people, it's considered maybe a little too re-identifiable, so we want to drop those entirely. So these are kind of things that are ideal to do in SQL, and we can do them in SQL. So in DuckDB, a SQL macro is just a way of kind of wrapping some SQL in a function. It doesn't have variables, doesn't have fancy things, but it's really just taking your basic SQL and putting it into a function. So we're going to create 2 functions here. One that looks for whether the country in the address is a US country or is the US. And then we're going to create a second one that does that postal code math where we take the first couple characters in the postal code, and then we exclude these specific 3-digit codes that have less than 10,000 people. And this is based on the US Census data and is a pretty common practice in anonymization. And now we just need to adjust our view definition. So we can use that kind of experimental invoke function, which was implemented for this purpose, to say, instead of saying that for each address, we're going to pull out the postal code, we're now saying for each address where the country invoked anon as USA, which is the function we just did, or is empty, those are the only ones we want to pull out the postal code for. This is a little tricky, right? Country empty should, may or may not be the US. It turns out that in most US-based hospitals, if there isn't a country, it means that the country is the US for an address. So we kind of take empty countries and treat them as US in this data set. Of course, different data sets you might tweak that. And we're going to rename the column to zip3 because now we have a 3-digit postal code, which is called the zip code in the US. And then we're going to, on postal code, instead of just pulling the path for postal code, we're going to mix in our SQL here and say postal code, this is a FHIR path expression, dot invoke, and then we're going to call our anonymization zip on the postal code to kind of reduce it to 3 characters or make it null if it's less than 3 characters with less than 10,000 people. We also need to do kind of 2 other adjustments. In the interest of time, I won't show the SQL here, but it's pretty straightforward SQL to run. We're going to hash our identifiers. So we're going to use the get resource key SQL-on-FHIR function, but we're going to invoke a hashing function on top of it. And here's where we're using a variable. This variable could be used anywhere in this view definition, but we're going to pass in a pepper from the command line. I learned a couple months ago that when you have an obfuscation value that you're applying to every record in a database that's the same, it's called a pepper. And if it's different for each record, it's called the salt. So we're going to pass in a pepper value here, which will be hashed with the IDs to make them a little bit harder to run against the lookup table. And then for birth year, we're going to do the same thing. We have a function, anon date to year, that we're applying to birth date, which is going to split out just the year. Again, like this is like 2 lines of SQL, but now we can mix it directly into our view definition. So let's go ahead and do this. So I'm going to take the view definition we wrote before, and I'm going to update it. Oops, let me just to the view definition we just looked at. So I'm just going to paste that in here. And we'll save that. And now we're gonna run. Oops, let's pull it up here. So we're going to run FlatQuack again. This time we're going to pass in our anonymization macros. So we need to tell it that macros are. Oops. So the reason I'm using an @ sign here at anonymize is these are built-in macros that are included in the distribution. You can actually pass in any file of SQL here. So you could just pass in 1 or more SQL files with your own macros directly on the command line. We're going to use these built-in macros, and we're going to run it here. It's going to pull down the package again, and we got an error. So let's look at this error because it's interesting. Here's what we forgot. We forgot to define pepper. So this is where having a full compiler rather than doing kind of some simple substitutions or using off-the-shelf SQL really shows its strength, because our parser has recognized that we're using a variable called pepper in our view definition, and we have not passed it in on the command line, and it's told us that's the problem we haven't done. So let's pass that in. So we can pass in a pepper value here. And you probably in the real world would want a very long random string here. I'm going to pass in ABC because we're doing a demo. So now we can actually run it, and hopefully we won't get an error this time. Okay, in 28 milliseconds, it has run our updated view definition. So we can look at our output CSV here, and we can see it's a little different from the one before. So now we have a hashed ID. This is not a GUID. It's a hash of the GUID plus our pepper value. So we've obfuscated that for the third party. Then we have, you'll notice the dates, the birth date now is only a year. So we've used SQL to kind of strip that down. We're still getting the birth sex, and now we have the 3-digit zip code as well. So this is an example of an anonymized patient list that we can now send to a third party. And we were able to run this directly on a pile of NDJSON that was extracted from the EHR without having to kind of write a lot of custom SQL to do that. We're able to do it in a form that's really understandable to an analyst or to somebody kind of working with the data. So let's flip back to the slides here and wrap up. So there are a lot of directions we can go in DuckDB. A couple of the things I think would be really interesting to pursue are expanding FHIR path support. So we support almost all of the FHIR path used in SQL-on-FHIR, but not some pieces that folks haven't needed in FlatQuack yet. I think value set integration is really high value. So right now you can pass in specific terminology codes, so like a list of ICD codes into your query, and you could do that by putting them into your view definition or passing them in at compile time by using variables. But I think it would be nice to have more features around being able to take a predefined value set of those codes and drop them into FlatQuack using something like the member of FHIR path function. As the query library capabilities kind of mature in SQL-on-FHIR, it might be neat to be able to both run a couple flattening functions and compile those into SQL, and then also compile the SQL that's going to work with them directly. And then lastly, and this is kind of a fun idea that I think that I've been experimenting with. I have a little prototype of this. Since FlatQuack has the full FHIR schema, we could also potentially potentially output FHIR instead of flattened data. And so this maybe goes a little bit against some of the SQL-on-FHIR ideas, but it's neat to have kind of dual purpose view definitions. So we could do something like our anonymization, but instead of outputting a CSV, which is what was needed in this case, we could output FHIR for cases where that's needed, but the FHIR with the transformed values. So it would provide another way to kind of transform FHIR. That's highly experimental and kind of a fun idea that I think is maybe worth playing around with. I put at the top that the next steps are up to you. So this is an open source project, and we're kind of happy to get pull requests of specific features that folks want to add, as well as, sponsoring development. So if there's something specific you want to see in FlatQuack, you can cover some of the development costs, and we'll make sure it gets into the open source project as well. And that's kind of how all the macro support and anonymization ended up in there as well. So thanks for the time. I'll post the link to these slides, and I think we'll have it up on the conference website as well. You can go to flatquack.org to see the source code, again, fully open source. There are a couple related projects that are worth noting. One is the FHIR Bulk Export API, which is a way to get NDJSON out of an EHR or a clinical system that you can use as the starting point for your flattening. There's a FHIR data quality project called Qualifier and an implementation that Boston Children's Hospital is maintaining. And these tools are really good because we all know that analytics, if you get garbage in, you're going to get garbage out. And then lastly, there's a set of sample bulk FHIR data if you want to play around with this yourself. And I put a link to that. That's also from the Boston Children's Hospital team. And you can run Cynthia, but there's also some bulk files that you can just drop into your project. So really appreciate everyone listening, and I'm happy that demo worked okay, and certainly encourage folks to play around with it. I think maybe we have 1 minute for questions, Arjun. And
I think we have 1 minute. There are some questions in the chat. I think awesome work as always, Dan. Love it. Super innovative. We did have a couple of questions about the FHIR to FHIR transformation ideas. So I don't know if you want to take 1 minute and describe them. So that seems exciting to people.
Yeah. So I think so. In a lot of these cases, right, the FHIR, what we're doing is pulling something from an element nested inside a FHIR, transforming it, and then outputting it. And so I think there's the opportunity to, instead of outputting it as the flattened item for that, output it as if it was still in that FHIR hierarchy. And this would provide a really good way also to filter down FHIR resources. So if you have FHIR resources that contain a lot of data elements, but you only want to send a few data elements to a partner or upload them to a data warehouse, it gives you that option of easily filtering kind of FHIR data using view definitions. This is something you can do today in a couple other ways. John talked about a few other projects that do this, including FHIR mapping language and Google's project, which I forget what that one's called. But there are a few projects that do this, but I think it would be nice to be able to reuse kind of existing view definitions in this way as well. So I think it's a fun avenue to explore, but pretty experimental at this point.
We recently discussed using FHIR patch operation to do stuff like masking and phishing.
Yeah, I think it's a super practical use case. I mean, you need to trim down FHIR resources, you need to convert them, data quality. So, all right, we are over time. But thank you, Dan. Really appreciate it. Great stuff. So